Okay, hi. This is the second time I've tried to do this video. The first time I got lost in coin flipping and probabilities and what have you. So I'm going to try to strip it down and do a better job of just getting to the essence of what's in chapter 10. I think a good place to start, though, is this quote on page 311 that I think actually can be used for the whole chapter. It is beyond the scope of this text to discuss details of statistical analysis with and without control variables. Proficiency in these areas is critical to impact assessment and should be represented on any evaluation team undertaking such work. That just means that, yes, if you haven't taken 3 courses in statistics and probability and regression analysis, then trying to do the type of impact evaluation that Rossi speaks of in some of these latter chapters in his book are going to be impossible for you to do. It's very much like being the executive director of a nonprofit and not knowing all the accounting rules or how you actually do accounting in the details. And as we learned in the financial decision-making course, as the executive director and CEO, you do not need to be an accountant. That's why you hire an accountant to do all the detailed work. What you do need to know, though, are some of the major concepts of finances and be able to understand conceptually, financial statements and read them and financial ratios, and be able to understand them and glean the importance of them so that you can lead your organization effectively. Well, it's sort of the same thing here. You don't need to know all the calculus and all the computer software and all of that other stuff that goes into arriving at the statistical analysis that Rossi speaks of. You just need to understand conceptually what's going on. So let's see if I can help you do that, okay? And this is really stripped down. Not going to talk about flipping coins and probabilities and all that stuff. Just going to try to get to the bare bones. Okay, so behind me, let's see here. Behind me there, sorry, I gotta move all my coins there from the first try. Okay, behind me here is a graph. Okay, and it looks like your typical bell curve, right? That within any group, if of randomly chosen people, if you think about them on any particular outcome, we're not going to say what it is, but there's a low score and there's a high score, and typically, most of the people are in the middle, are in the average, right? Over here, the frequency of the outcome, and so if you pick 100 people and you give them some sort of measurement, there'll be some people at the low end, some people at the high end, but most people are going to be in the middle. They're going to be average, okay? And so we'll just put that here, and we'll say that 5, for argument's sake, is the true average. Okay? But the other thing that's important to note then is, well, how close are people to that average? Are they widely dispersed around it, or are they fairly close? And the way that in statistics we decide if someone's fairly close to the average or far away from the average is by saying, what is a standard deviation from the average? And so they have this term called standard deviations. And it's a constant measurement. It can be different depending upon the different shape of the curve, but essentially, this is the important part. that within one standard deviation of the real average, either side, you capture 34% of the total number and 34% of the total numbers, so that within one standard deviation of the true average, you have 68% of the people, the scores of all the people. And if you go out 2 standard deviations, this is the second, minus 2 standard deviations, and over here we'll go out plus 2 standard deviations. This was plus 1, plus 1. This will be plus 2, plus 2. You get an extra 14%. Another 14% of the people are within, the measurement they got on some outcome was within 2 standard deviations of the true average. So now, with 2 standard deviations, you have captured 14, 68, 14, or 96%. It's a rounding error there, but you've captured 96% of the people. Okay? So, if you're thinking of, and so, that's how standard deviations are used to tell you kind of like, if this is the true average, well, within 2 standard deviations of that, 96% of the people will have fallen, in your outcomes. And so, if you then think about, okay, this was just a random group, they came in off the streets, I gave them some test, and they got some sort of specific outcome. Now I'm going to give them a treatment. Okay? And after the treatment, I get this sort of curve. Right? And I find that the true average is now out here by 8. True average. And so the difference, the program effect here, the difference between the true average before I gave the treatment and the true average after I gave the treatment is this amount here. Right? This is the program effect, and you can measure that in terms of standard deviations. Okay? And you can see here that the first standard deviation was taken to here, and the second standard deviation came to here. And so what you have found in your treatment is that if the true average is that you find it has come out to here, it's beyond where 96% of the time you would have expected people to fall. Okay? And because the average has moved so far, that the probability that you got this change by chance is less than 5%. And if it's less than 5%, that's where they say, oh, significant. Okay? Because the chance that you tested the same group after treatment and they got this score and got this sort of distribution, it could only happen by chance less than 5% of the time. Okay? Therefore, statistically, we say it's significant because we'll take a 5% error rate and say, yeah, we think this is really true because the chances of it happening just by chance and getting these scores just by chance, less than 5%. Okay? But it is 5%. And so sometimes, in this case, it says that, oh, it looks like there was a positive effect. But sometimes this is by chance. This is not the true average, it was just a fluke. This is where you get a false positive. Or what he calls in the book a type 1 error. Right? conversely, you may have had a bell curve that for some reason everybody screwed up that day on, on the test, and you got a false negative. In fact, it did damage. And that's a type 2 error. Did I do that right? I hope I did. Sometimes I get them backwards. Okay? And the way that you guard against getting this sort of mistake, where you think the sample has really improved by a lot, is by making sure that your sample size is large. And now I'll digress just a second. I did a coin toss earlier, right, with a coin. And you would expect that if I did it 10 times, I'd get 5 heads and 5 tails. What I actually got was, I might change this a little bit. Let's see. I had got, it was like this. Tails, tails, tails. And so what I got was 70% heads. Can you see that? Okay, I flipped the coin 10 times. In the first flip I got heads, second heads, tails, tails, heads, heads, tail, heads, heads, heads. So I did a sample, right, of this coin to see what the probability was, that it would come up heads. I know that it should be 50%, back like the example here on the board. But what I got was 70%. And if I didn't know what it should be, I would say, oh, well, I tried once. It was 70%. The true average was 70%. But if I flip the coins a lot of times, or if in the back in here, you think about if I only tested one person from the original group, maybe by chance I picked this person out here, who scored really well, but that's an outlier. It's not a true representation. So this talks to the notion of power in your sample and the power of your results, and goes then to the point that the more times you sample something, the more times you try something, the more likely it is that the results you get are actually true averages and not just outliers masquerading as true averages. Okay. Okay. So the last part of the last 2 sections of the chapter, he talks a little bit about subgroups. And what we've talked about here is everybody. Those 100 people who walked in and you measured them on some outcome. It may be that some of those groups actually did higher than the overall average, and some of them did less well than the overall average. And when you combine the 2 groups, they in fact, give you the total average. But it may be, that some groups really did have an average of 8. Some groups had an average of 2. When you put them both together, you get the average of 5. And so it's important to look at subgroups when you're thinking of the effectiveness of your programs, because maybe some subgroups react differently to your treatment or have more or less, quote, deficiencies or a baseline, a stronger or weaker baseline at the beginning of the program. Okay? And then just lastly, when they talk about the meta-analysis, they're talking about you have your study and you're trying to figure out if your treatment improves in a certain dimension. But you're not the only person who's ever tried to do this. And so there are many studies out there that have looked at the same problem, thought about how to make the improvement, and have done, pre and post test and randomized experimental designs, and come up with, the original average and now the new true average based on treatment. And meta-analysis just compares all the results of all of those studies so that you have, a range of likely outcomes. In other words, if I'm a teacher in first grade and my kids improve by 2 grade point averages or 2 grades in reading, okay, that sounds wonderful. But if I do a study of all the first grade teachers in the whole country and everybody has a 2 grade point average, or 2 grade increase in reading scores, well, then I'm not so great anymore. I'm just average. And so essentially meta-analysis and looking at all the studies that have been done on a particular problem and a particular type of treatment in order to get a particular outcome you want gives you then a benchmark against which you can compare yourself, not only to see how relatively well or relatively poorly you're doing, but also it's if you get a score that is tremendously different than everybody else's, then either you have an incredibly bad program or an incredibly good program, or probably more likely you have a problem with your experimental design in the evaluation design, and you're getting type 1 or type 2 errors. Okay? All right, 16 minutes. That's it. Hopefully that worked for you. If you wish, please call. Be happy to speak with you about it. Okay? Thanks.